Alright guys, so what we're doing today is we're finishing up the note sheet from yesterday. So we're going to finish that up and you will get your assignment for today. So, not too bad. So this is where we stopped yesterday. Now when we look at this here, so we have something called set builder notation, and that's what this is. Set builder notation gives us a way to describe numbers and types of numbers in an easier way or fashion. Now there's a few main components to this. So we have the set of all real numbers x. So this here is really telling us our number types. I may have said classifications yesterday, but it's telling us what kind of numbers are we looking at. Are we looking at natural numbers, whole numbers, real numbers, integers, rational, irrational? What kind of numbers are we dealing with? And this here is kind of giving us a description. Well, it could be that all real numbers greater than 4. So x is greater than 4. It's telling us more information about what number types we have or what the group is. So this is the type of numbers, and this is kind of giving us a description, more information about it. And that's really all there is to this. Now, if it is all real numbers, we're just going to use brace x bar. We don't have to put anything else. But if it's a number type that's not all real numbers, so if we're just talking about the integers or the natural numbers or the whole numbers, we have to specify it. Now, before we delve too far into that, we're going to utilize it doing graphing. Graphing inequalities on a number line is going to be the first thing that we're going to do. So when we look at this here, the first one we're going to have is A. For all values of x, or all real numbers x, such that 2 is less than x is less than or equal to 5. So really we're just graphing the inequality. 2 is less than x is less than or equal to 5. So you've done this before, you did this in Algebra 1. So how would we start going about graphing this inequality here? So we would have a mark at 5 and 2. I put circles to kind of signify we have those spots. And we use circles because it could be opened or closed. If it's open, it is not included. If it is closed, it is. So would these both be open, both be closed? One open, one closed? 5 would be closed because it is equal to. We have less than or equal to, so it would be closed. But the 2 would be open, not equal to. And then what do we do next? If x is in the middle, we shade in the middle. Because the values of x are going to be greater than 2, but less than or equal to 5. They're going to be between the two. When x is in the middle, we shade in the middle. And that's it. That's all we have to do for this. Questions on this here? We good with this one here? Awesome. Let's look at the next one. For all real numbers x, such that x is less than or equal to 0, or x is greater than 4. Right, we would fill the 1 in at 0 because it is less than or equal to. Anytime we have equal to, we will fill that in. So let's look at this here. X is what? Less than or equal to. Because it always opens towards the bigger number. So 0 is bigger than x. So we would shade to the left or to the right of 0. Left. So if x is less than or equal to 0, so all the values less than or equal to 0 will make that statement true. Or x is greater than 4. So at 4, we would shade to the right. It won't always be that way, but most of the time it will. There are cases where or can go towards each other. If two or statements do go towards each other, we shade towards each other, it's going to be all real numbers. Because with an or statement, it's either one or the other. It could be one or the other. Could it be both? Well, yeah. Because with an or statement, it means one of these must be true. And if it was going towards each other, well, where they share, they're both true, so it does hold true. We would have to make a specification. There is a type called conditional or statements where it has to be one or the other. It can't be both. That would be considered a conditional or. So with most or statements, it could be one or the other or both. It could be both. And it has to be both. For an and statement, it has to be both. Now, most of the and statements that we will have at this point will come in this form. Later on, we will have and inequalities where we'll have to make sure we're shading where it isn't common, and we'll go over that when we get there. All right. C, for all values of x such that, for all real numbers x, such that x is less than -2 or x is greater than 0. So again, -2 and 0, they'd both be open because neither one of them is equal to. You don't have equals on either one. So -2. So let's look at this. X is what? Less than -2. So we're talking about all the numbers smaller. Or x is greater than 0. So they're going away from each other. Most of the time when we have or statements, they will probably go away from each other, but it's still good to check to make sure that is the case. Because I have set these up, especially on the review sheet. We worked them out, and it worked out they both went in the same direction. So it's always good to check and make sure. Any questions on A, B, or C? Okay. Do we feel pretty comfortable with graphing these inequalities? Yes. We'll look at one more. It doesn't matter which one because these look a little bit different. We don't actually have a number line. Yes? Now, depending on the teacher, I think for most of y'all, Miss Kendall and I are about the same with this. I am not going to make you draw a number line out and have, okay, here's 0, and then actually try to put it close to scale. I'm not going to make you do that. You don't even have to put 0 if 0 is not one of the two numbers. So when we look at this first one here, number 4, well, what are our main 2 points? -6 and -2. So this is what I would do. -6, -2. Because those are our 2 key points. Because at this point, we know what a number line is, so having the rest of the numbers doesn't really help us too much. Doesn't tell us anything else. The one key thing that I will deduct points on is if you set it up like this, I will mark that wrong. Right, because smaller numbers go on the left, bigger numbers go on the right. We just have to set it up properly. Okay. At 6, we had to have a and shaded. Now, if you notice, I do kind of a little swoosh around the line. I do that so it's easy to see what is shaded and what is not. Because it's sometimes hard, especially with a pencil, trying to color over the top of the line, because it blends right into the line itself. So I do this just to make it a little bit easier to see, and you don't spend a whole bunch of time trying to shade really dark over the top of it. I think it's easier. So are we good with this here? Awesome. If we're good with it, we will move on. So this here, we're going to be dealing with actually writing set builder notation. Now, what we cover in here is a way that you can write it. It is not the only way, because the ways that we can write and put sets and set builder notation oriented. Depends on how you want to do it. So, and I will show you, especially with the first one, the different ways that we can do it. I'm going to start off with the way I like best, and then I'll show you some of the other ways and what the textbook has. Now here we have the set of all what? Integers greater than 5, yes? Now with set builder, this will stay about the same. We have brace x. And as we saw a minute ago, we were writing kind of the definitions and looking at it. That's what we started with, and then it hit bar, because it said x bar and then our statement. Now this here, because we also were looking at it, it said when we have it that way, it's the set of all real numbers x such that. Well, here we don't have the set of all real numbers. We have the set of all integers. So we need to define x as not a part of the real numbers, but it's a part of the integers. Now the way that we do that is with this e. It looks a little bit like the prongs of a pitchfork. There you go. And what this is saying x is an element, and then we'll use our symbol for integers. So what we're saying is x is an element of the integers, or x is in the group of integers. This element is just a member of a set. Because we define the set of integers, so everything that is an integer, we're saying x is one of them. We don't know which one in particular, but it is contained in that set, in that group. So x is an integer. So we've gotten that part done, yes? Well, we need to give it a little more definition. We just need what? So x is greater than 5. And that's it. That is it in set builder notation. So for this here, it's not too much more different than what we had already, but I think it looks a little bit cleaner than having just straight words. As long as we know what the meaning is, x is an element of the integers such that x is greater than 5 for all real numbers. Now, the textbook, what they will say is for all real numbers x such that x is an element of the integers and x is greater than 5. It doesn't change anything. It's the exact same thing. I think the reason they're sticking with this here is because really it's leaving this part the same every single time. You're just going to stick with that and then add the clarifications and details on the other side. I like the first one because it's a little bit more succinct. This is the type of x we're dealing with. These are kind of more clarification. So any questions on this here? Okay. If there are no other questions, or if there are no questions on A, we'll go on and look at B. Now B is that, what type of numbers are we dealing with there? Or let me clarify, are we talking about natural numbers, whole numbers, rational, real numbers? Because natural numbers would be 0 and greater, or 1 and greater. So that would work for part of it, but not all of it. Because integers, so is pi contained in this? So that would be irrational, so that's also included, right? Is there anything really not included? So we would be talking about the real. Because whenever we have interval notation, kind of like what we wrote yesterday, we're talking about the real numbers. We're talking about any number between those groups. So this here would be all real numbers. So when we write it, well, we can just go this right here. Because we're talking about the set of all real numbers. Well, that's what that is. So we don't have to put any clarifications since we're talking about all real numbers. there. Now in here, we normally want to try to stay away from interval notation and set builder notation. Can we have it in there? Maybe, but not normally. We want to stay away from it. So we have the set of all real numbers x such that, well, this here we're talking about x is what, less than -1, yes? So that's what that part is. So we can say x is less than -1. Or, what else? Greater than -1.
But where's our infinity?
So here, so x is less than -1 for the first part, so it's any number less than -1. So in interval notation, we need 2 spots because we always have 2 numbers in the interval. Now, if it is unbounded, where I only have 1 endpoint, so our endpoint here is -1. Well, it's unbounded, so it's going to continue on to infinity. So we need it for interval, but in our inequalities, it's understood x is less than -1. It's going off to -infinity. X is greater than -1. It's going off to infinity. We don't have to include it. And we have this here. Let me get a different color. We can actually write this simpler. Because we're talking about all real numbers, yes? Is there any number that would not be contained in this set? There is one. So -1 to infinity, would 0 fit in here? Well, yeah, 0 is greater than -1. So that doesn't work. So -2 would be less than -1. Well, -1 is -1 less than -1. Is -1 greater than -1? So what is the only number that doesn't work? -1, right? So why don't we say that? Because I could say that this is the set of all real numbers x such that x cannot be what? -1. Because it's only 1 point, 1 spot where it doesn't work, we can say it's everything except for that number. Questions on this here? And again, this only works if we have a point. Now, if it had been, instead of -1, if this had been, say, +1, then it wouldn't work as well because we do have all the numbers between -1 and 1. Because then those would have to be excluded. But that's it for that there. Any of these would work. Any one of these here would work. Questions on this so far? Well, let's look at number 6. We have -infinity to -1 or 1 to infinity. Yep. Yeah, so we do have different 1 and -1 and 1. But also, what happened at -1, we don't have a parenthesis, we have a bracket. So that means that -1 is included. So again, it is all real numbers, so that makes it a little bit easier. So we can start off with our brace x bar, the set of all real numbers x such that what? We can start off with this inequality. X is, what would we say? Less than or equal to -1. Yes. Or Again. And that's it. Any questions on any of this here? Are we good with all this so far? Okay. Let's look at number 7. This one's normally what y'all like the most out of all these because of the except for -4. Now, we'll start off with our normal. Brace x. We would use RE. And then to see with the line, our integers. Such that. Is not equal to -4. X is any integer except for -4. This here is the last thing we'll cover and take notes with. There's a few things we'll talk through. But this here is, we can use set builder notation to do this, or we can just use sets. And the main reason that we'd use one or the other is how easy is it to write. So if we wanted all the whole numbers, 50 through 54, well, what are they? So we'd start at 50, 51, 52, 53, 54, right? Well, heck, that's not bad. We can do that, right? You go 50, 51, 52, 53, and 54. So I'd write it as a set. I mean, we have 5 numbers. We can just write it as a set. It's not that bad. And that's it. That's all we'd have to do. That is the set. Well, that is the whole thing, because only whole numbers are just those, like our natural counting numbers. We don't have decimals, we don't have fractions, irrational numbers. We don't count any of the numbers in between. We're just counting those. Because if we wanted to write this in set notation like we did previously, we would say x is an element of the whole numbers such that 50 is less than or equal to x is less than or equal to 54. Wait, is that any more simple than writing 50, 51, 52, 53, 54? Not really. I'd almost prefer just to write the 5 numbers out and be done, because it gives us the exact same thing. So if we're able to really just write them out, it's 5 numbers, 6 numbers, something easy to do. Let's just write the numbers. That is the set. It is in set notation. We use set builder notation if it's something more than that, something that's hard to write down, or we're not able to write it all down because I don't want to do it. So we good with the letter A, problem A. So problem B, okay, so the real numbers 0 through 4. So I mean our first one would be 0. What's our next number going to be? Well, our next number would be 0.000000001, and then 0.0002, because we're not talking about just the whole numbers, we're talking about all the numbers in between. The decimals are rational, irrational numbers, everything. So it would be 0. You got it. Is. Well, since it is all real numbers, we don't need it, because this is the set of all real numbers x such that 0 is less than or equal to x is less than or equal to 4. Because we only need to do the e if it's something other than all real numbers. Okay, because since it's all real numbers, I don't want to have to list out every single number between 0 and 1. Also, I wouldn't live long enough to be able to do it. Because if you can think of the millions, billions, trillions, quadrillions numbers that we can put out, all I've got to do is put it over 1 over, and all of those would be fit between 0 and 1. Well, there's an infinite number of those, so there's an infinite number of numbers that we can fit between 0 and 1. I don't want to list them all out. I'll probably die trying if I did. But that's all we have to do for this. Because it's not something we can easily list, we'll go with set builder. Now the integers from negative 100 through 100. Now this here is not as many numbers as the last one, because we have, I believe it's 201 different numbers between these two. But I still don't want to write it out. That'd take forever. So again, I would stick with we do. The bar is after. Yep. So we use x element of the integers to kind of define the numbers. Since we don't have all reals, we have integers, we've got to clarify that first. And then we would use negative 100 is so it'd be less than or equal to technically, but and that would be it. Questions on this here? And yeah, it's a little, for some reason, it's easier to draw the first one than it is to draw the last one. Questions on this here? Now, y'all can probably see it in the notes already. The next one that we have is the prime whole numbers. There's still, most mathematicians consider or kind of go back and forth if there are more whole or prime numbers, if there's going to be a place where we get to numbers big enough that the prime numbers don't exist anymore. Essentially, we get to numbers so big that they're going to have factors. There's some that think that it will, some that think that they won't, and it's kind of going back and forth. But there is a theorem called the, man, why did I just lose it? The Riemann's Hypothesis, which, if proven, would kind of let us know either, yes, there are more and more prime numbers no matter how big we get, and it would give us a way to actually find out what they are. And most likely, even if it did come out, the government, most governments would cover it up anyways. Because high-level security systems use 27 plus, and maybe not even that small, digit prime numbers. Because the only factors of a prime number is 1 and its self. So if you really wanted to get to that number, you had to you really have to have the number to be able to get in. Unlike other numbers, if you can have the factors to make it up, you can eventually get to that number by getting at the factors. So having huge prime numbers, over 20 digits, is good for security. So if they were able to actually find a way to figure out what the prime numbers were, it wouldn't be good for most security systems. So if you can figure out a 50 plus digit number that is prime, you could probably sell it to someone or a government agency for a lot of money and have you forget what that number is. Yep, but to be able to do that is very time consuming to try to run through every possible number because, yep, because the bigger numbers you get, the gaps between prime numbers is quite large. and they've kept a lot of them, especially the really big ones, under lock and key because they don't want people knowing them. So the chances of you finding a new one might be a little slim at this point. But prime whole numbers, now we're just going to talk about this because this and some of the other ones in the note sheet I find not that interesting, and you'll see why here in a second. Because if we were to do this, well, x is a whole number such that x is a that's it. X is a prime number. Yeah, I don't find that. I mean, essentially, you're just rewriting the statement with braces around either side. It's not really doing much. I mean, it'd be the same for integers and whole numbers, natural numbers, and rational numbers. So I'm not too concerned with that. But this is your homework assignment. So on page 7, 5 through 14, 17 through 24, 26, and 27.